Now that we've gone through some of the theoretical underpinnings of comparative cohort method, we've gone through a study that did a good job of it. We've spoken about all the threats to the validity of the estimates it can do. We're going to now go through some of we're going to use the Odyssey tools, or a couple of the Odyssey tools that have been created to do this. And so I'm going to go through images of the tool that just identify where you would basically point and click wherever you have to make an analytic decision to actually implement a full study. You've seen this before. We just read it and tore it apart. And just as a reminder, our target cohort is dubicatrin new users with prior atrial fibrillation compared to warfarin new users with prior AFib. We're going to look at the outcome of stroke from 1 day after the cohort start date to the cohort end date. And the model specification is 1-to-1 propensity score matched conditional Cox proportional hazards model.
Hey, that's very interesting how you define the time of risk.
Yeah. So
do you always define it relative to cohort start name?
you can define the time at risk however you like, and you can pick as a reference point the cohort start date or the cohort end date. So you could say something like time at risk is 1 day after cohort start date until 10,000 days after cohort start date, and that will look for a person's entire observation record. Or if you've defined your cohort to have a cohort end date that is the end of a persistent drug era, the cohort end date would be variable for each person. It would be the amount of time they've been persistently exposed to a drug. So in this case, cohort end date is the length of the prescription or length of multiple prescriptions provided to have been within 3 days of each other.
And does your censoring events happen in your cohort definition or your time at risk definition?
The tools are flexible enough for you to specify it either way. So you can specify it so that you can put censoring events into your cohort definition, or if you create your cohort definition with a cohort end date that's later that a censoring event happens in the analysis, then it can do it at that point as well. You can, if you want to go to this Atlas instance and click through a little bit as we go, please feel free.
Actually, those URLs are not this year's URL, right?
No, I changed it. This is the correct one. So if you want to go to PLE population level effect estimation .odyssey tutorials .amazingwsdemos.com, you will be able to go to Atlas. Do you want a minute or two just to look at this?
Yeah.
Yes. Okay. So Atlas, for those of you that are familiar with Atlas, I apologize for the repetitive, for being repetitive, but for those of you that don't, Atlas is a very, very flexible tool that is used to make doing many activities in informatics and epidemiology much easier. It's an integrated environment where you can search the complete vocabulary, search many medical term vocabularies. You can create code sets and concept sets from the items in the vocabularies. You can then use those concept sets in conjunction with logic to create cohort definitions and identify patients across a whole network of databases. You can then use those cohort definitions as the inputs to characterization, prediction, and population level effect estimation studies. So you kind of start at the lowest level of creating concept sets of medical entities, and then you use them to identify patients. You put them in cohorts and use that as inputs into these standardized analytic routines to generate these three kinds of evidence. And like how anyone did anything before something like Atlas is tricky. You know, like you used to remember phone numbers and now you no longer do. It's kind of it's sort of like that for epi analysis.
So the
Yes.
second
Yes, so this second link is for is for RStudio. And RStudio is an integrated development environment for R, and we will have access to that, and there are logins available. I don't know how much we're going to be using it right now. Let's focus on Atlas for now, and if we get there and we want to try executing a study package, we can, but that's a little bit down the line. So anyway, so that's Atlas. Does anyone have any questions about just the super high level of Atlas? This is a user interface for doing a lot of stuff. So here is the description of the cohorts. And so we've already gone through what they are. There's new users of dabigatran or warfarin with a series of inclusion criteria. And so in Atlas, what you would do is click on the left, you would see a section for cohort definitions. And when you go to cohort definitions, you have the option to do something called create a new cohort. And you would do that, and then you have this first section called cohort entry events. So this is your very, very initial criteria, the first thing that you would use to identify a patient in a cohort. So in this case, we would say, this patient has a drug era of dabigatran for the first time in the person's history on or after the study start date of October 19th, 2010. You would say that they're greater than or equals 65, and that they have 6 months of prior continuous observation time before the index date. And so that is how you would first find your new user, or your new user per this definition of dabigatran. And once you have this anchor, this will be the index date. This will be time 0 in your subsequent analysis, or the cohort entry date. You can then apply all of your subsequent inclusion criteria in order to further reduce that initial set of people to those that you're interested in. So for example, our study has prior atrial fibrillation or atrial flutter diagnosis, no prior treatment of the comparator drug. You don't want someone that's already been on warfarin in your dabigatran group. No prior treatment with other anticoagulants, not in a skilled nursing facility, et cetera. All of the criteria that were in the paper. And then each one of these inclusion criteria has you specify very similarly to how you specify the cohort entry event. You would say prior atrial fibrillation or flutter, and you make those, you include those inclusion criteria relative to the index date. So we would say that this patient, a patient has to have either, so this, you see where it says having any, that basically makes an or condition of these two boxes beneath it. So we say of those new users of dabigatran, they need to have either one occurrence of atrial fibrillation all days before, up to, and including the index date, or at least one occurrence of atrial flutter all days before, or up to, and including the index date.
Can I set up an index date?
So you do that in the previous step, in this cohort entry event. So it's funny, yeah. We don't say index date anywhere here, and that's for good.
The era start, that date is the index start date.
Yes. So it's like once you create that initial anchor, it's against that anchor or index date that all of your other inclusion criteria are relative to. And you can say, and these additional inclusion criteria, you can make them relative to the start date of the index event, or even the end date of the index event, depending on what your index event is. In our case, our index event is a drug era. So the era has both a start and an end. So we could, if we wanted to, for some reason, define this, apply inclusion criteria to this dabigatran new user group by defining something by a cohort end date. Obviously, in this case, it's not what we want to do, but the tool is flexible to do that. Thank you, Chris. Chris implemented the ability to add your inclusion criteria off of the end of the index event, which basically made my life a whole lot easier in a study we did a while ago. Yes.
Cohort you're showing guys, is it you the list?
I don't know. What is this?
Actually, we looked for Davi as a pre-created cohort, and I don't think it was there in the demo environment.
I don't know. Martine will make one. Yeah, so each of the inclusion criteria, then you you're able to specify and make those criteria relative to the index event. And then lastly, you have this cohort exit criteria. And this again takes us back to that definition of a cohort, which is people that satisfy one or more inclusion criteria for a duration of time. So you need to have the beginning and the end. And we've created as the end of this, the cohort end date for this group to be the end of continuous exposure to dabigatran, provided the day's supply of the, if there are multiple days supply of the drug, it's considered continuous exposure if the beginning of the second era happens within 3 days of the end of the first era. So again, like Martijn said, that's a pretty restrictively small gap. So many people might not have a day's supply that ends within 3 days of their new supply starting. So, yes?
This is kind of going back to the baseline period discussion, because if you are using drug eras, then there's already some calculation. And if your drug era calculation is based on day supply plus something, which I can't remember, is 30 days what they say is the default drug era?
I can clarify this.
Yeah. You are right.
Right?
Yes.
I don't mean to.
No, go ahead, please.
So the entry of the cohort was based on the eras, right? So only the start date was used for the cohort entry, okay? You're right that the end date of that event will be based on 30-day gap windows and individual exposures. You're absolutely right. However, all we're doing is saying they entered when the era started. At this point, we're not looking at error records anymore. We're looking at the individual exposures that happened around, for all time actually. And he's specifying that I'm going to make new errors out of those exposures where the gap is 3, not 30. So while the error was built off of 30, we don't actually look at the end date of the error anymore. We just know one thing that both these things agree on: the error started at the same time. It's just how long they persisted.
Yeah, this would have been more clear if that initial event criteria, actually, if I changed that to a drug exposure.
Correct.
Drug exposure of dabigatran, because then there wouldn't have been any of this confusion about how errors are made. Because yes, we've overridden the standardized approach to creating drug errors in order to make this design similar to the approach they've taken here with that smaller gap days between subsequent day supply.
If you go back to the first page of this plus.
That's this one?
Yeah, right. Basically, the age criteria has been added to the first row or whatever, first section. But can we put that into the inclusion criteria?
Yes.
That's
Yep.
a possibility?
Yeah, you can, any of these inclusion criteria, you can put in various places throughout the tool, and that's really so that you can evaluate the impact of different inclusion criteria on the patient counts that you end up getting. This study is not going to be done unless the patients are greater than or equal to 65. So we don't really care how many dabigatran users there are in total, and then how many of them are older than 65. In this case, that's just part of the initial event criteria, because that's defining them. But we do want to know, for example, maybe how many have these other events. This is actually a very nice tool for clinical trial feasibility. If you want to know what the impact of various inclusion criteria are on a base population in the real world, you can do this, and then you can count and see if you were to go and do a clinical trial, how many patients you would lose or gain depending on your definite criteria.
We just added the gray and cohort definitions to the tool. You should be able to see them now. Odyssey, your tutorial, but the right one.
And then as we're using the tool to build these cohorts, we need to just bear in mind that every entity that's referenced in a cohort definition needs a complete definition of concepts and associated codes. So it's like when you create any of these criteria, atrial fibrillation, that box atrial fibrillation is referring to a set of concepts of medical entities that the ultimate query that this thing is building will go and look for in the database. So in the cohort building tool, you can just click on this tab that says concept sets, and then you'll see the complete set of concepts concepts used to build the query that grabs these people for use in your analysis. Then, as Martijn said earlier, once you've built one exposure cohort, your target cohort, if you want your comparator cohort to be all the same except for the index drug that you're exposed to, you just copy it. Press copy, you get a complete carbon copy of the first cohort that you've made, and you just change the first criteria from dabigatran to warfarin. And now here's here's how you would design the outcome cohorts. So in this case, we're interested in, it's like the first occurrence of a ischemic stroke. So again, ischemic stroke, because it's a blue box there, it refers to a concept set, a set of codes that's meant to represent these events. And we've specified that the condition type must be in the inpatient position, inpatient primary position. And so there's primary, first position, and then the visit occurrence has to be in the emergency room or in an inpatient setting. And then there's just a closer view of all of that stuff. So once you've built these cohorts, we've now built our T and our C and our O. We now use these cohorts as like the building blocks to construct a comparative cohort study. And so you would, on the left-hand side of Atlas, just move down from this cohort definition section to the estimation section, where this little arrow is here. When you click that, you'll see a page that says new estimation study. So when you click that, up comes this screen. And this is divided into 3 sections, the estimation study. There's the section where you specify what the comparison, or what comparison or set of comparisons you're going to do in your study. The next is the analysis settings. That's how you intend to balance your T and your C cohorts, and how you might and how you want to specify your outcome model and maybe further restrict your populations based on some other decisions you have to make. And then lastly, there are the evaluation section, and that's where you specify the diagnostics that you're going to use to see if you've got a valid comparison that you could use to get a trustworthy estimate at the end. So this comparison section is you would put your T and your C and your O and a set of concepts representing your negative controls. Because not only, as we spoke about earlier, we're interested in comparing and looking at the comparative risk of stroke between the dabigatran and the warfarin group, but we also want to look not only for ischemic stroke, but we also want to look for a large set of outcomes that we don't believe will be caused by either of those drugs. The idea is that if our design actually produces a null result on many of those negative controls, then we would expect the result it gives us on ischemic stroke to be closer to its actual, like closer to the truth. I think we'd call it calibrated. So when you would click add an outcome. So there's where you add your target and you add your comparator. And what you would do is you just click these little file boxes, and then it will bring up a list of cohorts that have been previously built in the tool. And you would just search query for the cohort that you built. You could name it whatever you like, and when you search there, it'll come up, and then you add it to the target cohort. You do the same for the comparator cohort, and then you add a concept set for negative controls. The idea is the reason that you don't actually add cohorts for the negative controls is because you want each negative control outcome to be built the exact same way, and there's actually a template SQL that you can make you can specify it how you like, but what it will do is it will then go and create outcome cohorts for each of the concepts that you've added in that list. So it's not like you need, say you have 60 negative controls, you don't need to go into your cohort builder and build 60 negative control outcomes. The package functionality will do that for you. You just give it concepts. Yes?
Include logic. Like, I thought concepts were just codes. lists.
Mhm.
But can you include logic for each of those negative control definitions?
So like you can do whatever you like, and you could make your outcome logic quite sophisticated for the negative control outcomes. What comes out of the box, what's in here by default, is some SQL that looks for basically occurrences of the code. Is it over? What's the gap between the between?
There's a gap there. Usually just the first occurrence. So you do have some options for how you turn the negative control concept into cohorts, but it's primarily you take the first occurrence of that code anywhere in the patient's record, including any of its descendants.
I think you have the option to do. I think the option for first versus like first ever versus first post index event is in there, isn't it? No. Okay. First, so it just gets.
I don't think you can. I think Martin's right. I don't think it knows anything about what index is when you're creating the negative controls. So, but it's possible there's an option to allow multiple.
That's no. That's what I meant. And if you get for your negative control outcomes, you get multiple events. Then later in the analysis, it'll.
You can decide to throw away those.
Right. But I guess I'm probably wrong. But this is where you add it, and then so your comparison includes your T and your C, and in this case, we've added 2 outcomes. This has a GI bleed and ischemic stroke, and but then importantly, it's in this section where you also need to add a set of concepts that you do not want to use when you are fitting a propensity score trying to make these two cohorts comparable. The idea is that if you were to include as covariates to go into your propensity score model, covariates built from the same concepts that were used to create your T and your C cohort, then you would actually fit a predictive model predicting that predicts assignment, that predicts membership in the one cohort using details about that cohort as the predictor. And it doesn't make sense. If you want to predict dabigatran class membership, but you're using dabigatran in your predictive model, your predictive model will do very well, and it will perfectly separate those groups. It'll say, I know exactly who is in the dabigatran group. It's these people that have taken dabigatran. So like you need to specify, and like that's kind of obvious when it comes to like don't use the actual concept for the drug that defines the index date in there. But then there are often like proxies that perfectly will predict your group. So sometimes there's a little bit of figuring out which other concepts will create covariates that are basically proxies, perfect proxy measures for your T and your C membership. So it's in this case that you need to specify them so that they don't muck up your model.
Yeah, but don't worry about if you get it wrong, because then when you run the code, it actually will just throw an error at you saying this is too perfectly predictable. You probably want to take out these variables, but you won't see that until later down the line. So this is a consequence of the way that we use or we construct propensity scores, which is we throw in basically everything that's in the data, and we also include the index date itself. And the reason why we include the index date itself is that's usually where the most important information occurs, like the reason why they're getting the drug and other information that the doctor finds important to document at the time that they're getting the drug. So because we throw in everything and we include the actual index date, you have to explicitly exclude basically the stuff that's the thing that you're measuring, the treatment assignment.
And to note, that is a best practice. That is a best practice to include the index date when you're creating these covariates. But the tool is flexible enough to say you're really convinced that you don't want to include the index date. You can specify a look-back window for your covariates to look 6 months until -1 day before the index date, and you can do that. But the default is set to include that index date because that's when the action happens, or at least a lot of it.
Yeah. So.
Go ahead.
So we have a default set of covariates that usually ends up being somewhere between 10,000 to 100,000 covariates that are constructed off of the data. There is an option. Can you go back to one slide? There is an option here, covariate selection. Oh, no, sorry, that's
We're
later
gonna
on.
get to it
Oh, yeah.
later.
Where you can modify that default set as much as you like, but the recommendation is to not do that, to just use the default set. You could do exactly the same thing that Graham did and just include, what was it, 50 or maybe less covariates that they used. Or you could use our approach.
But before I move on, when we say, oh, we are just building 100,000 covariates, does that make sense to you what we're doing? We've got a large cohort of people in many cases. Say you have 100,000 people in the cohort. Then you have an entire vocabulary worth of concepts. These are concepts that represent all sorts of medical entities, or conditions, procedures, drug exposures, blah, blah, blah. And what you do is like the feature construction approach takes your list of, say, 100,000 people, and then it takes all of the concepts that could possibly exist in these different domains, and then it looks to see which people have these concepts in their record before their index date. And when you have hundreds of thousands of people and hundreds of thousands of codes, the numbers that you can get, the number of covariates that you can get across this population can be quite large. And so it's like you think of what you learned in Statistics 101, where you get a square data set with rows for people and columns for covariates, and they're like 20. So like this ends up being 100,000 rows. It's not stored as 100,000 columns. So it's not stored as 100,000 columns, but it's like that's how you end up with these huge numbers of covariates to characterize populations. Is that clear? Make sense? Or mud? So after you've specified the comparison that you're interested in, you move along and you specify the analysis settings. And the analysis settings on this first page, you can see add analysis settings. So if you want to do multiple versions of your analysis, you can. If you want to match on the propensity score, you would specify it, and then you say, oh, but I think that I want to trim the extremes of my propensity score, because those people with very large or very small propensity scores will unduly influence my effect. I'll add like a sensitivity analysis. So you would click the button and have another analysis setting where you would then re-specify your propensity adjustment strategy. So when you click on the analysis settings, you get these 5 options for study population, covariate settings, time at risk, propensity score adjustment, and the outcome model. And so the study population setting are a variety of decisions that you make in order to restrict your initial cohorts down to the people that you will be interested to put into your propensity score model. Say for, like, we've been speaking about how we want to think of cohorts as these discrete units of people that can be used in multiple studies, used across the board. But say for your study at hand, you're only interested in looking at a study period from 2012 onwards. So you would use your reproducible cohort to start as entry into the study, but then you could specify a study period in this place where you would only use the people in the cohort that are that happen to have their cohort entry during this particular window. Should only the first exposure of the subject be included is a way to decide whether you can have a person enter basically be included in the analysis for each time they enter a cohort. If you remember from our cohort definition earlier, a cohort can have a person enter and exit again at multiple times. For our purposes here in the new user cohort design, we're just using their first cohort entry only. So in this place, we've specified our cohorts in a way that won't even allow us to have multiple entries. So this particular setting is not even necessary.
Just interrupting again.
Yes.
So maybe important to explain why this is. So we do have a lot of options here that you could equally enforce in the cohort definition. And so the reason why we have it both here and as an option in the cohort definition is just it depends on what you're doing. It might make sense to do it in one location than the other. If I wanted to do a sensitivity analysis where I want to, in one analysis, want to restrict to the first use, and the other analysis I want to take all use, then probably I don't want to do it in my cohort definition because then I'm stuck with it. Then I would do it here in one analysis and restrict to the first use in one analysis and not restrict to the first use in the other analysis. And the same is later on, I think there's an option, do you want to exclude people that are in the other cohort, so exclude people from the dabigatran cohort that are also in the warfarin cohort. That's just something we already did in the cohort definition, but we could have just also done it here, but because we're not going to change that in any of our analysis, we just choose to do it in our cohort definition. So there's flexibility here. That's what I'm trying to say.
So whenever you see, it's like, oh, here's an option to do something where I already had an option to do it before, it's because, well, sometimes you might want to do it both ways, and having that flexibility is nice. This next decision that you need to make is what Martijn just mentioned. In our cohort definitions, we made sure that there would not be people that are in both the T and the C cohort, so this decision doesn't apply to us. But in many cases, you might have people in both cohorts. And say, for example, somebody starts on the T, starts in a T cohort, is exposed to some drug, but then they switch to the C cohort. And the question is, what do you want to do with those people? There are three options. You can just get rid of them altogether. If there's a person that's in both cohort, don't include them, period. There is keep them in both, where they will contribute time at risk to the first cohort until they enter the second cohort, at which point they'll contribute time at risk to the second one. Or there's the last option of keep them only in the cohort that they enter first. So only include in the model the person in the T and not in the C. Any thoughts on why you might make those decisions? There's a really intuitive one and I don't think there's a study on it, but the idea of keeping the patient in the cohort that they enter first is, it seems intuitively better than dropping them out altogether, because in the situation where someone might switch from T to C, it probably means they're switching because T is not working. So that person is probably more likely to have the outcome, which is why T is not working, so they switch to C. That person might be more likely to have the outcome than someone that doesn't switch at all. So if you were to just drop them from everything, you would basically be making a healthier population out of your whole study, which would move your effect back towards the null. So that's one situation where you might choose to keep first. But then again, sometimes you might want to keep people in both.
So I know the flexibility is awesome,
Mm-hmm.
but you might have a censoring event or an exclusion criteria. I guess couldn't be exclusion criteria because then you're using forget that. You could have a censoring event that if they take warfarin, then they're censored.
Yep.
But then you could also do it here.
Well, it would be moot at that point, because if you've built your censoring event in your cohort definition, you would never see the person. You would never see the person in both of the cohorts. Oh no, wait. No, I see what you're saying. Yeah, it would. So in that case, it would, no, but.
So if you're doing stuff like that, plus if you're trying to do a sensitivity analysis, how do you know if these ones are going to override or the original ones that you wrote in the cohort?
So see down here at the bottom, it says, if a subject is in multiple cohorts, should time at risk be censored when the new time at risk starts to prevent overlap? So that option is what you would use. You would not build the censoring event in your cohort definitions, and then you would say the keep both section here and say yes to that lower one, which would allow it would basically, you wouldn't have to censor your cohorts. You would have your cohorts would be free of a censoring event of the other drug, but then you would build it into the analysis here.
Okay, so that's how you would do it for the censoring piece. What about for the sensitivity analysis where you do more than one prescription?
The sensitivity analysis where you want to what? Just keep them in the cohort they entered first?
You want to only look at the parts of the cohort that have at least 2 prescriptions. And you would do that here, right? The minimum number.
So that 2 prescriptions, you would have a new cohort for those people.
Oh, this creates a new cohort.
No, what you would do is you would just have another comparison. So back at the beginning where we said dabigatran versus warfarin for the outcome of ischemic stroke, we would then say dabigatran needs two subsequent drug exposures versus warfarin needs 2 drug exposures for the outcome of ischemic stroke, whatever.
But I thought you said don't do it in the cohort if you're doing a sensitivity analysis, because then you're stuck with
So I think we're mixing up two things now. So specifically in the Graham paper, they had this sensitivity analysis where they restrict their cohort to people that have a subsequent prescription. So that's not something you can actually do here. I'm just was talking about you could do a potential, not a new user design, but just a prevalent user comparative cohort design. And so that's something you could do here.
So then there are a couple more options here. There's a minimum required continuous observation time before the index. Of course, we already specified that in our cohort. So again, there's an option to do it here if you want to vary that a little bit.
Which one will override which?
Study settings always have the last word.
Yes.
But if in your cohort you're saying I require 6 months, and then here you say I require 3 months, well, you already got rid of the people that had just 3 months, so that's not going to have any effect anymore. So it is a sequence. So you first have your cohort definition, and then you apply these criteria. If they're more strict, then you're going to lose people. But if they're less strict, then you're actually not going to lose people anymore.
And then
You can't reverse a decision in settings that the cohort eliminated up front.
Yes.
You can't reverse it like, oh, I said 3 months in my cohort definition, but over here I'll let 6 months come in. Your cohort definition didn't have the 6 month people to include.
And then what the software does that's very nice at the later, once you start outputting various objects, is you get an attrition diagram that shows how many people you lose for each of these decisions. Then you end up saying, oh, I lost no people for this decision I thought really mattered. And like you learn something. So covariates for confounding adjustment. We went through the handful that they selected to use in their study. Here you would click covariate settings and exclude. Here we are. So when you click that the covariate settings, you get these options, and there are checkboxes already included on it, which are the default covariate settings. And what they do is they look for things like sex and age group and race and ethnicity, and then for covariates that are not static like that, you can select these look-back windows. So we have long-term, medium-term, and short-term options, and then end days. And end days is what you can think of as the upper bound on the look-back window for covariate selection. So that day is 0 because we believe that stuff that happens on the index date is actually important for predicting treatment group membership, target comparator membership. So we've included that. If you don't want to do that, you would change end days to -1. So what it means is these long-term covariates would be looked for in the 365 days before index to 0 days before index, or the index date. For medium term, it would be 6 months, and for short term, it'd be 1 month. And anyway, once you have those settings, you would then click in the boxes below to create conditions, condition groups, drugs, drug group, and then all of these other different domains of information where the feature extraction package will go and create these features for all of the people in both the T and the C cohort. And then those covariates actually are what are then subsequently used in the propensity score model to do the balancing that we spoke about earlier. And then there are a couple of these indices down at the bottom too, where you can create a CHADS score or a DCSI or Charlson index. Yeah.
Down at the bottom, you have long-term checked and short-term checked, for example, for procedure. Are those mutually exclusive, or they overlap?
They will overlap. They'll overlap, and then the particular regression that's used in fitting the propensity score will sort out which one of the two is actually the most predictive and retain it.
The coefficient from it would take into account that every time you had long-term, you also had the short-term.
Yes. Yes. So like that kind of doubly robust estimation is from what I understand, it's fitting a model to predict like target versus comparator membership is actually a different task than fitting an outcome model later. And the idea is that the covariates that are used in fitting the propensity score might also provide additional adjustment in the different model later. And that option, again, is available here to do it if you want.
Would you doubly robust?
Yes?
If I try to run the document, I think, okay, so I got the error of high correlation compared to error.
Yep.
Then, so I have to adjust the use setting, or do I have to impose more baseline covariates?
We need to think about what those covariates are. If those covariates are basically proxies for your cohort definition, it's probably safe to remove them and say, oh wow, well this is really just a proxy for the definition that defines these two groups. But it might be that, oh wow, these cohorts really differ on this or that characteristics, maybe so much so that they're not comparable. So it depends on what the covariates that come out of that high correlation error actually are.
When you click in negative 365 days, our cohort definition was a minimum of 180 days.
Yep.
So for some people, if you just meet the minimum, you're not going to get the full 365.
Yeah.
Is that a problem?
Might be. Mitch did all the look-back window research, as far as I know.
I mean, your models will fit. If you have only a baseline requirement of 180-day look back, but some people have more than that, some people don't. And so you'll go back to 365 among those people who have it. But if you, for example, don't, maybe you have 0. But your models will still converge. There's potential validity problems if it's really systematically different across the groups. But my experience is that things don't vary widely enough in real analyses to cause problems. But your models, it won't create like a model fit issue. It's an interesting question. My interpretation of asking that.
Okay.
So the nice thing about using propensity models is that you're just trying to predict treatment as best as you can. And so it actually doesn't matter as much what these features represent. So the fact that you may not observe some features 100% accurately is not really that meaningful, as long as if they're predictive of the treatment, they'll end up in the model. And so the fact that you may have slightly misspecified your look-back window, and that not everybody will have that 365-day look-back because you're only requiring 6 months, that actually won't affect you that much. It just means that maybe those covariates will or will not end up in your propensity model in the long-term window.
So then once you've finished specifying which covariates you want to use in your propensity score model, we then move along in these analysis settings to start thinking about your time at risk. And the time at risk, you have a couple options. You need to first determine what the minimum number of days of time at risk available, it must be available for follow-up. And then next, you specify your time at risk either relative to the cohort start date or the cohort end date or both. So in our case, in the cohort definition, we've actually built our cohort end date into the cohort definition, which ends at the end of persistent drug exposure, and then those are stitched together if the end of the first one is less than 3 days gap between the beginning of the second one. So in this case, our time at risk start would be 1 day after index date, and our cohort end date would be 0 days from cohort end date. If you wanted to do something at a 30-day biologic window on the end of your persistent drug exposure, because the idea is that the effect of the drug will persist for another 30 days, you just add that on here. Did they do that as a sensitivity analysis in this? I don't think so. Yeah, that's just a common one where you can put it in here. Here's where you specify the propensity score. Do you want to trim your cohorts on the basis of the propensity score? No. What do you want to do with your propensity score? Do you want to match? Do you want to stratify? Or do you want to weight? And we've said here we want to match, and then beneath that we say the maximum number of comparator patients that we will match to the target patients. As say in this point we say 1 because we want to do a 1-to-1 match, and then we specify the caliper, which is basically the range of propensity scores for a comparator patient that we will say is acceptable to match to a target patient. And then we specify the scale on which that caliper is set, which is the standardized logit of the propensity score in this case. And again, these are the default parameters. You can change it to whatever you want.
Because actually, the Graham paper doesn't specify the use of a caliper, but we just, it's a default option, and actually it's probably a good idea to do it anyway. You don't want to match. If the closest match is somebody really far off in terms of difference in propensity scores, you probably don't want to include them anyway. So it's preferred to have a caliper. And I don't know what Graham, whether they did or did not do it, because they didn't mention it in their paper.
And then the remaining options in this section are ways that you can fine-tune the large-scale regularized regression. That is the engine for the propensity score generation. And for example, there's a setting here of don't bother using more than 250,000 patients if your cohorts are larger than 250,000 patients, because you don't get any additional bang for your buck at that point. And there are more details of the lasso regression down in the bottom that we can talk about later if you like. Yes?
What's the trimming fraction you refer to? If you say yes, like trim by %, they could ask you to specify a trimming fraction.
So what fraction of the population do you want to trim? Do you want to trim 5%, the lowest 5%, and then the extreme 5%?
Symmetric, like it won't be asymmetric trimming.
That's right, yeah.
Okay, yeah.
And then lastly is the outcome model, where in this case we have a conditional Cox proportional hazard model, conditioned on the match sets. And down in the bottom is where you can add some additional outcome model settings, like it was asked back here. If you want to add covariates into your outcome model as well, you can do so below. But if you've got good diagnostics from your propensity score, you might not want to. And then lastly, we have evaluation settings, and it's in this place where you specify how your negative control outcome cohorts are going to get built, and then how you will use those negative control outcomes to create synthetic positive control outcomes, which is what Martijn spoke about earlier, and that will give you a whole range of known answers to the question, which you will then use to calibrate the estimate that you're actually interested in. So we will now specify a design, and we'll know its operating characteristics on a bunch of outcomes that should be no difference. That should be a 25% increased risk, 50% increased risk, a two times increased risk, and a 4 times increased risk. But you can set those known effect sizes to whatever you want. But that's a nice default. And when you're finished doing this specification, you get to look at the total number of analyses, or the number of estimates that you're going to produce. Like we did, we had 1 T and 1 O, and then, 1 T, 1 C, and 2 O's. So that's 2 effect estimates, because we only did 1 analysis setting. But if we'd added more analysis settings, or more T's and C's, or more O's, those things would all get enumerated here. And you end up with the number of estimates that you end up with at the end is it's the product of the T, C, O's, and the analysis variance. And if you're really if you're not too sure of a lot of your analysis settings and you want to try many of them, it explodes into a very large number here, and you end up with like lots of different estimates that all reflect all the different choices that you've made in your various analyses. And at the very bottom, you click Download Study Package, and you get a zip file, which is an R package. And in this R package contains all of the code necessary to execute this thing start to finish with the press of a button. Any questions before I go into the kind of architecture of the R program that comes down?
Well, maybe if you could briefly go back to the outcome model. Sure. Because I think actually people brought this up, I think it's several times now already today, this question of, well, we're focused very heavily here on the propensity model, and we're actually not saying much about including variables in your outcome model. And so you brought that up, like if I want to plug in age in that outcome model. So I have this principle that I'm trying to call Martijn's power principle, difference principle or something, but maybe I shouldn't take ownership of it. But one important thing to realize is so we can adjust for variables in two places, in the propensity model and in the outcome model. Propensity model, we have lots and lots of data. Like Graham had 70,000 people in each cohort, right? That's, or 70,000 in one and 270,000 in the other. That's a lot of data, and you can fit a very nice large model without any problem. The outcome model usually are severely underpowered. Like, I don't know, we had maybe a dozen people that had the outcome and the rest didn't have it. So the model that you can fit at that end is usually much more limited. So you can include one, maybe two extra variables if you're lucky. But I prefer to put all the weight on the propensity model and keep the outcome model as simple as possible, because you want to preserve all that power to estimate just one thing, which is the treatment effect. So it's preferred to just throw everything in propensity model because you have lots of data usually there. And then if you pass all the diagnostics, probably you're fine in having just a very simple outcome model. But you could you could actually include all of the covariates that you include in the propensity model again here, which would make it a doubly robust analysis. But we've implemented that and observed that actually is probably not a very good idea. Like our negative controls actually show more bias if you do that than if you don't do that.
You surveyed any of the papers and see how often they do double robust versus not? Like, have you ever done a search to figure out like how often they one way or another?
No, but you do see a lot of people that they throw variables in the propensity model and they throw variables in the outcome model, and like there's no justification for it.
What I generally see is that if there are one or two covariates that are unbalanced after propensity score adjustment, they'll say, oh, those ones must be the ones we should also put in the outcome model.
But that's not true, right?
I don't think so, but it's done.
Well, and there's a lot of implementations of doubly robust methods, right? Like, I think that, well, sorry, Actually, I have a question. Can you bootstrap, would there be anywhere I could say, like, I want to bootstrap my confidence intervals, or would that be something I do in the R package that I download?
Bootstrap?
Like empirical confidence interval calculation. So, I mean, the way I would do it would be, I would take my study cohort and randomly select people with replacement from it. I basically do 1,000 of those, estimate 1,000 confidence intervals, and take the distribution. My understanding is anytime you do doubly robust estimation, you would have to bootstrap your confidence intervals rather than estimate them using like a closed form.
Isn't that downstream after you?
I think so. That's why I'm thinking maybe it's something I would have to do in the R program.
Yeah, that's certainly not cooked into this, but like you could do it.
Got it.
So this is kind of along the same lines. We have not done any diagnostics yet.
We're going to look at them momentarily.
Okay, so you download the study package first, or in Atlas, can you, like, we need feasibility to see if we have any people in our.
Right. So the ways that we would do that, when we built those cohorts, first of all, what we would have done is gone to the next page and clicked generate, and then it will just build them on the spot, and you can see if there are 100, 0, 10, 100, or 1,000,000 people in your cohort. So like that's the first way that you would do it. But all of the diagnostics, the whole suite of them that we've spent all day talking about, will get generated by this study package that we download. So when you download the study package, you make sure that a very important setting is set to true, which is called blind. And you say blind equals true, which means you will not see any effect estimates at the end, but you'll get the whole slew of everything else. And then what happens, why don't we look at it? So you click download study package and you save it, and then you open it up, you open up your R instance and you open up the R project, whatever you've named it. And this is the anatomy of the study package. So the study package includes these 4 sections. It's got the cohort section, and what it is it has the JSON representation of all of the rules that you specified in that earlier cohort definition section for your T's and your C's and your O's. And then it has the SQL versions of that. It has, when you click through that cohort the cohort definition UI, what's happening under the hood, thanks to our friend Chris back here, is that every time you press a button, it's building the SQL that will actually find exactly those patients in the database. And just think for a second the amount of flexibility that's in that UI, the amount of stuff that you can do, all of the different time points that you can peg off. You can't think up something that it won't do. And anyway, it just writes the SQL for you and it stores it in the study package. And then next, it has the negative control concepts, all the concepts that you believe are not caused in any way by your target or your comparator exposures. And that, you can get from this common evidence model that we spoke about earlier. And then it has the SQL template to create all of those outcome cohorts for them as well. And then it has all of the settings for your positive control, synthesis. And that's how you can make the sort of like known larger than one effect sizes that you will also use to calibrate your effect estimate later on. Has your analysis settings. This includes all of the T, C, and O combinations that you've specified, and then the definitions of all of those choices that we made in the analysis, in the study populations, analysis settings, time at risk, and propensity score settings are all stored as another JSON object. And these JSON objects are like nice and transferable. Like say someone across town's got an Atlas instance, you just send them the JSON and plug it in, and there's the whole design for them too. And then lastly, there's the execution code, which is something that you just specify. You put in your database connection information, like what the database name is and any like user credentials and passwords, and where you need to write to. You have to be able to write to your database in order to create these cohorts. What happens is the SQL that you've written by pointing through that UI will then get built and build cohorts on a writable space on your server, which is then used as the input to all of the analysis later. And then lastly, there's a Shiny viewer. Are you familiar with R Shiny? It's like a really nice, easy, interactive visualization tool in R that you can use to navigate this whole slew of stuff. And then here's in the R package, and then in the R package, there is this is where these are the folders that all of the stuff is saved in. How do you install it? You open the package. We just spoke about this. You have to build your R package. So once it's opened, you need to press this install and restart so that it's stored on your machine so that your R instance will know where to look when you're running things. Or you can get it from GitHub. If there's an R package, if there's a study package that's on GitHub that you want rather than one you've made yourself, you just download it and go. Then here are the few lines of code. These will install all of the dependencies, these are all of the other R packages developed by the Odyssey community that you need to have loaded on your machine in order to run the complete study package. Once you do that, here is the few lines of code.
So just to point out, all the code he's now showing is actually inside of that package, so you don't have to write that down and memorize it.
Yeah, there's a hilariously obvious file in there called code to run, and you just go to that, and there it is, and then you run. Except you do have to fill out some of the information that's on this page here, like your connection details to the database that you're going to hit off. And then once you actually execute the whole thing, this is the data model. These are all of the results from this analysis are all put into this very standardized data model. And the reason that this is standardized like so is that you can use this in the Shiny app. And then you can take an estimation study that someone has created in one place and an estimation study that someone's created in another place, and you get all of your analysis in the same format, so you can put it into the same viewing software and view all of the diagnostics for any study. And yes, it can be shared. This doesn't include any patient level information. And then lastly, you click the Shiny app, and off you go. Do you want to take a look at what one of these Shiny apps is, the results for a complete estimation study? Do we have time to do that? Okay, so here's one. We were talking about clinical trials and observational studies yesterday. Here's one where we tried to predict a clinical trial before it ended. And this is just a landing page that doesn't come right out of the app. But the app looks like this. This is not blinded. Pardon? Oh, sure. I don't know. Oh, yeah. Is that large enough? Okay, so if this one is not blinded. So for example, here we see hazard ratios. Sorry, if I make it a smidge smaller, is that okay? Is that all right? So you see where my mouse is right now? These numbers would all be blanked out if this was blinded, because we would not want to look at the hazard ratios or any of the calibrated hazard ratios until we were confident that our diagnostic tests have passed. So just let's pretend we don't see any hazard ratios there. So what we would do is we would take a T. So here are all of our exposure cohorts. Oops. And then here are all those exposure cohorts again, and we pick the two that we're comparing. In this case, it's unicompartmental and total knee replacements. This just happens to be a study I did recently. And then here are the set of outcomes: venous thromboembolism, postoperative infection, readmission mortality, opioid use, et cetera. Beneath that are the number of data sources that this was run against. This was run against 5 databases, and then we did a random effects meta-analysis where appropriate. And then we had all of these different analysis specifications. And these analysis specifications have different time at risk periods because we had different time at risks for these different outcomes. Our complication outcomes, we were interested in a shorter time at risk, and then our revision outcomes, we were looking in 5 years. But the idea is that you click through these, and then you get more of your results. They all show up down here. So I've got one database worth of effects, or worth of results rather, for unicompartmental versus total. And what you would do in order to go and check the diagnostics, say we want to see the diagnostics of our primary analysis on this outcome of venous thromboembolism. We click primary, and we get this set of tabs that beneath shows us all of the final results. So this power here, we've got, this is a 10 to 1 variable ratio matching. So we have 7,779 unicompartmental patients, and then 58,290 total knee replacement patients. And note, this is after the propensity score matching has taken place. If we wanted to see how many people we started with, we'd click on the, oh look, it's not there. We usually have an attrition table here. This one doesn't, this was an older, one of the older ones, I guess. One of these tabs would actually be the attrition table that I spoke about earlier that shows how you lose patients as you go from your initial cohort size down to the bottom. My apologies, it's not here to look at. Anyway, we see that of those 7,779 unicompartmental patients, we see that there are collectively 1,200 years of follow-up time. And then during that follow-up time, there are 165 events for an incidence rate of 132 events per 1,000 person years. And we have the exact same information for the comparator group, 58,000 people, 9,200 years time at risk, and 1,900 events for an incidence rate of 214 events per 1,000 person years, with a minimum detectable relative risk of 1.2. So if we didn't see any of these hazard ratios up at the top, we would say, oh, we have enough people and enough events to at least detect an effect of 20%. So it's okay. And then beneath that is the time at risk. And we had a 60-day time at risk for this particular outcome. So you can see the max is 61 because we set it to go from the day after index to 60 days farther. So that's why the maximum number of days is 61. And then
The number of events observed in the target versus comparative group in the interval specific. Is that right?
Yep.
Sorry, MDRR?
Oh, did you say the IR?
No, the MDRR.
Oh no, the MDRR. That's a power calculation given this the minimum detectable relative risk that you have the power to detect, given the number of events and the people that you've got after you've made all of your decisions to get into it.
Yes, so usually when people do a power calculation, they're in the frame of mind of a trial, and so they have a suspected effect size, and then they say, I want to have an 80% power, and then how many people do I need? But in observational research, that doesn't make sense because you have a number of people, And then we just say, okay, so these are the number of people that we have, and so many outcomes are observed. This is for 80% power. What would be the smallest effect size that we could detect? So it's reversing it and basically.
So if we went through this whole exercise and we got here and we said, we have a minimum detectable relative risk of 5, we'd say, yikes, what have we done that's thrown away so many people and events that we've lost enough power to detect a smaller relative risk than that? We have a hypothesis. We're worried about changes on the order of, I don't know, 50% or twice increased risk, but our minimum detectable relative risk is 5. You have to go back to the drawing board and figure out where your criteria for inclusion into the study has thrown away all these patients that make it hard to detect something smaller than that.
So I've never powered this before. Is there like a standard error equivalent that you use the default for calculating the MDR? That like, because you're saying 80% power is like, I guess the default that they're using for the MDR calculation, and then
Yeah, the defaults are.
risk, relative risk is like the standard effects of, but like, is there like a standard error? Like it doesn't translate like that, right? I never powered this on, so I don't even know what there is or consider. How does it work?
Yes.
So this is assuming you use a 95% confidence interval and then 80% power.
5% alpha.
5% standard error?
Yeah, 5%. Yeah, 5%
No,
alpha,
alpha.
5% beta, 20%.
The other way, but yeah, alpha 5% beta, yeah. Okay.
Another, I think, important thing is that usually when people do power calculations, they do it off of like the raw cohorts.
Yeah.
Like that doesn't really make sense. So this is computed based after you do the propensity score matching.
Yeah, I just wondering if there's like considerations for iteration. I don't know. Anyway, it's fine.
But remember, this is the type of thing we're supposed to be looking at before we see any hazard ratios up there.
Yeah.
So this would all be fair game to like, oh wow, our design is such that we do not have enough patients to detect a relative risk that is in the ballpark of what we kind of need to know.
We should even go forward.
So yeah, so that would be one place to say, by this design, we're unable to do something reasonable. So then this next tab is the type of thing you'll see in a table 1. There's one of these in the Graham paper, except this shows both before and after covariate balance for a pre-specified set of items across these various areas. So this has some basic demographics. It has age, sex, general medical history, including all of these conditions. And you can see that before matching in this particular study, there were some considerable differences, like a standardized difference of 0.17, 0.15, 0.2 almost. So this is the before matching differences in these like kind of canned set of conditions and prior drug exposures. And again, by these, like here's 0.21. It doesn't.
Yeah, so just to be clear, that this is just we're showing a subset of all the covariates that we actually constructed, because you can't put 100,000 covariates in a table like this. You can actually see them later on in a graph, but not in a table like this. So
this table is here to basically quell the requirements many people have to have a table 1 that they can see. When really a nicer way to look at the complete set of covariates, both before and after balance, is in a plot that's more like this, where each one of these dots represents one of those thousands of covariates that was created to use as input in the propensity score model. It's not actually the case that every one of these covariates was used in the propensity score model, but after the model decides which of the covariates to use, then you can test the balance on all of them. And as you can see, before matching, we have something like, no, this is like kind of buggy. Let's look at this one. Oh no. So what happens is if you mouse over one of these, it's not working because it's zoomed in, but you actually see what the name of the covariate is, and you can see it's before matching prevalence and it's after it's before matching standardized difference between the target and comparator cohort, and then the after matching. And what you see is that on the x-axis here, this is the before adjustment. You've got covariates that have a difference of up to 0.4. You got a handful around 0.3 and 0.2, and then a whole lot of them that are down around here. But on the y-axis, this shows the standardized difference after matching, and as you can see, there aren't very many of them higher than 0.05. And that 0.1 criteria that Peter Austin says and everybody likes about like being basically negligible difference is met nicely in this study. what's
but it's met nicely for like the 50,000 dots that are in here. So that's actually,
all of them.
I think,
And-
pretty cool.
And what's actually cool about this is see all these ones over on the right. It's kind of buggy because I'm zoomed in. These are all like imaging. These are all imaging concepts, and then you can see exactly where these imaging concepts are over on like the tail of the unicompartmental group. Because basically, if you're going to get only half your knee replaced rather than all of it, they go in and look a whole lot more. So it's kind of a nice, it's nice correspondence between the actual content of the covariates and then the look of this propensity score overlap.
Are you changing the structure of like the coefficients when you start working now?
We don't put one out without this now.
Okay.
Yeah.
But you can't publish a table 1 unless it's just like, here's a subset, right? Like, I mean, you don't do table 1.
So basically in our results section, we say, here's the link to this app that shows everything. And because the editor wants table 1, it's like farther down later.
But yeah, so the main reason why we actually have that table 1 here is because people want to see that. I'm not sure how well, I guess it also,
No,
it does give you a little bit of a better,
The table 1 gives
Yeah,
you
it does
good
a little
face
bit of-
validity, and like you don't, and the covariates included in this table 1, like here it's just a default set. But if your study is about a particular therapeutic area that's got a lot of interest in this, you could change to put your covariates here that give you face validity. Although, again, you're cherry picking a little bit already.
Yeah. But I mean, certain journal or
Yeah.
editor groups are very familiar.
Yes. But anyway, so like here's the good covariate. Here's the nice covariate balance visualization that kind of shows the majority of it. Here's the subset of it for some face validity type approach, and of course there's the propensity scores that we were looking at earlier. And for this, there's a decent amount of overlap, except all this extra imaging happening in the other group. And then here is the systematic error. So this is cool. So what these plots we've looked at a little bit earlier today. In the upper left panel is the uncalibrated estimates of the negative controls on the negative controls, and then the panels to the right are the estimates on the synthetically generated positive controls. And as you can see, it's like these are a little, on the negative controls, there's a little bit of bias to the left of one. You can see how those negative control estimates aren't quite clustered around the one in the middle there. They're a little bit left, and then as the known estimate gets stronger, the effects are a little bit biased towards the null as you get farther away from it. And then down below, after you use the characteristics of the empirical null and the empirical positive control distributions, you can use that to calibrate all of your other estimates. And then down at the bottom, you can see that the operating characteristics that you might expect improves. So like above, we have 70% of the confidence intervals include 1, but after we calibrate it, we get much closer to that 95% that we expect. And then lastly, when you're worried about your proportional hazards assumption, you can look at your Kaplan-Meier curve here. Yes. Yes. But anyway, so this is it. And then what you would do is, after you examine, so you wouldn't see a Kaplan-Meier plot when all of these are blinded, but you would get access to all of these other tabs, and it's on the basis of that you could make the decision whether you think the estimates you'll see will be valid or not. And then you would click unblind, and off you go.
So it automatically does the calibration and all of those things up front. It does all the balancing first. But basically, it runs the whole study. This might take weeks.
It depends on if you're running Legend, it'll take a while. But
And then after all that time, then you see whether you did it, whether you got enough power, whether you got.
yeah, so what the practice is, we're trying to push this approach where basically all of these diagnostics should go into your protocol. And really the protocol itself is a document that includes all of the methods and how well those methods work for your particular problem, and it includes almost everything except the estimate at the end. And like that's what you publish and you post and you say, here's the study that I'm going to do, and here's how well it performs. Do you agree? And then depending on, there should be no more to do after that.
And if you do the first one blind, then if you have to do it again or make adjustments or add.
Yeah, you haven't looked at the answer. You haven't hacked if you see an answer and all of a sudden I think something's wrong. So is it because something went wrong, or you don't like the answer, or no one knows anymore. So you keep it blind so that you're not cheating.
And if you run it blind, do you have to run the same hours?
Yeah.
So
No.
unblinding is really literally unblinding. So the results are actually already sitting in your database, in that data model, but the app is just not showing them. So you just need to restart the Shiny app, which is a second of time, with blinding set to false, and then you can see them.
Like you have the option to be unethical if you want, but you shouldn't.
But so to your point, like running the study package, like actually quite often it's just a matter of maybe half an hour or something. But like if you have very large cohorts, it can take hours, and well, in some really extreme cases it can take days to run. But it's compute time. It's not, you can do something else while the computer is busy.
So I'll torture you with one fun tidbit from this study that touches on this calibration approach is this one right here. So this is comparing unicompartmental to total knee replacement for postoperative infection. And there's been a whole slew of, actually Danny spoke about this yesterday, there's a whole slew of studies that show the risk of postoperative infection is lower for unicompartmental knee replacement than total knee replacement. There's one trial on this. It was underpowered to tell you anything about postoperative infection. So really all it is a whole handful of observational studies plus a meta-analysis, and that meta-analysis says that there's a risk. So when we go and do this, you can see that our hazard ratio is we have a 30-something reduced risk of postoperative infection with a highly significant p-value of a confidence interval going from 0.52 to 0.85. And that is exactly in line with all of these other observational studies that have been done and the meta-analysis of all of those observational studies. But what none of those observational studies did was calibrate their designs and take a look at how those studies will create estimates for negative controls. So here, when you look at what it looks like on negative controls, you see that, oh gosh, it looks like the people that have got unicompartmental knee replacement have got a reduced risk of all of these other conditions as well that should have nothing to do with either of those surgeries. So if you actually then go and calibrate the result against this distribution, you see that our calibrated hazard ratio is now 0.8, which is closer to the null, and a hazard rate in a confidence interval that goes from 0.5 to 1.25. So were all of those other observational studies that showed a reduced risk of infection, was that to the truth or bias? So like now we have one study that does a new method that suggests it's all bias. Yeah?
How can I run the model on the multiple data sources and
You do it. So to run on multiple data sources, you do it multiple times. You just, in that code to run, you would just add your connection information to multiple databases and just do it in a row. And then the meta-analysis just has some extra code. I don't think that's built. That's not part of the package that comes out from Atlas, but it's pretty straightforward to do.
And the software for the one data folder and the Shiny can be like applied on the
Yep.
folder.
Yes.
Can you input to the Shiny app, like the directory that you want to read from?
Yep. Yeah. So that's it for implementing one of these studies. And have any of you been playing with Atlas as we went through this? Yes, one. Yeah, so anyway, the concluding remarks here are just a couple items. Is that this cohort method, whoops, what have I done? There. Yeah, the concluding remarks is like, this is So like this estimation editor that we pointed and clicked through is really just a user interface for this cohort method package that's, the brains behind which are in a room right here. And cohort method is a really, really like flexible package to do this type of stuff. And most studies that you'll probably have to do can happen. You can use the UI to specify cohort method to do a lot of the stuff that you'll probably have to do it. But then there are also very, very unique snowflakes where you might have to do more add analysis specifications that aren't supported by the tool. But that's why the whole thing is based on R, because R is hyper flexible, and you can just output the package and then get in there and make the changes that you need to support your unique snowflake of a study. And this 80/20, I think, is just pulled out of a hat, but it's used in a lot of other Pardon?
How many publications in Atlas in this approach have been involved in?
A whole bunch. I don't know.
Like papers and methodological papers? Like
Both,
Yeah.
quite a long list.
50.
so you can come with a novel idea and then
Yep.
go through there and there's people who will accept it.
Yeah, so this one that we're just looking at, this guy right here is under revise and resubmit right now at Lancet Rheumatology. So like this one's gonna probably be like we just resubmitted a little while ago, but there are dozens of them. Like,
Do you reference the app? Like, when you publish, do you reference the system you used in every publication?
all of these packages have like developer credentials on them, although I haven't seen it used. It should be. You guys deserve more credit for it.
No, but there are some papers that are fundamental to basically some of the ideas that are incorporated in there. Some of them we usually use in reference to, like the large scale propensity score that they have developed.
And then in the software all comes with like reference material. It says like what every single function does and what all of the parameters in it are supposed to do, and then a reference to the papers that the thing has been designed because of are all included in it as well.
So with the exception of the Optum, I'm not familiar with all the databases that is, and I've heard of Legend, but I don't know what it is. So how do I know what's the data?
So Legend is a particular study. It stands for Large Evidence Generation. Yeah.
Large scale evidence generation and evaluation in a network of databases.
So that is a. You were at the symposium yesterday? Yeah. So they spoke about that. That's not a database. That's a particular implementation of a method against 15 databases. So like all of these other databases, Optum, as you said, is like American commercially insured insurance claims type database. CCAE is another version of that. Medicare is a older population of supplemental beneficiaries too, and there are lots of observational databases, and provided it's in the common data model, you can point this stuff directly at it and off you go. And that's the idea of these network studies, is that if you design a study that you want to get in, you need an answer to a question, but you have access to one database. You create this study, you get that study package, and then you can send it to anyone in the Odyssey network who will execute it against their data and send you back the results in that nice format, so that then you can just look at them in an app like this. And the idea is that's network studies are kind of the way of the future, and that you'll get to see what sort of heterogeneity of effect you get across large populations of people, and you stop making inferences, like grand inferences on the basis of a study in like one tiny little population. You can do it in many.
So a couple questions, and this might be more database specific, and I don't know who the appropriate person is to correct. Has there been any use of HCAP or HRQ data, like nationalized registries of claims databases besides Medicare?
Yeah, I mean, HCUP's converted to the CDM. We have a version of it sitting at Janssen. You haven't used it much.
No, but it only has. I don't think it has. It only has drug exposure, drug information, not so much the.
You have costs and comorbidities and DRGs, but only limited on the inpatient cohort. The ambulatory ones kind of very restrictive. So
And also, it's just hospital visits, right? It's not. You don't see them across hospital visits. So yeah, there's not much you can do in terms of.
What about the SEER, Medicare combined? Do we have anything that is more cancer relevant stuff?
I think that at our shop, the Flatiron data are being converted to the CDM right now, aren't they? Isn't that
Yeah.
what Molinero's working on?
And Laura told me that Senior Medicare will soon be.
Yeah. Yeah.